Aló, aló. Aló, aló. Aló, aló. Aló, aló. Sí, ya me lo explicó. Seguro. Gracias.
Pero tiene que prenderse la luz, ¿no?
No, la luz no. Se prende el...
Sí, es en el otro, ¿no?
Sí, en el otro.
¿Empezamos ya?
Faltan 5 minutos.
Yo tengo y 58.
Faltan 2 minutos. Tienes. No. 3 minutos.
Yo te quiero dar 2 minutos más.
No, dame los 5 minuticos, Gloria. Dame los 5 minuticos. No, después.
Voy a sentar adelante, Claudio, para que no digas que no oí tus pláticas.
Good afternoon. Welcome to the afternoon session. We are going to start with Claudio Mendoza, who is going to talk about atomic data.
Well, good afternoon. I would like to thank the organizing committee for this kind invitation and for allowing us to share Gary's company in more pleasant environments than an airport lounge. And also to be with friends, colleagues who go back to my student days, and also to young people who you probably met on the beach rather than in an astronomy center. Okay, I'm going to take it on from what Christoph was talking about to do with the database, the atomic database that Clodudy has, and something that we really have to be certain is that this database is reliable enough for users to be able to do astrophysical modeling. I mean, to get to that point is an extraordinary effort. And also for them to share the same database, this is a very practical thing, because that means that the differences are to do mainly with the models rather than with actually using different data sets of the atomic data sets. However, this is effort. This is a very admirable thing that Gary and his colleagues have done. This is a very difficult enterprise, and it's full of problems. For instance, this task is reserved to experts. The master data set becomes outdated even before it's released. The process is expensive and it's difficult to sustain in the long term. The new atomic data are not taken into account until they go into the code. It's error-prone. Experts, are not 100% experts, so they can make mistakes. Very difficult to actually decide which database is better than the other. It's a problem of time. There's hardly any feedback between or from data producers, data collectors, and the data get discarded. Once a new one can arrive or they're in the actual databases, they are displaced. So this is a very difficult task, and to do this in time is, like I say, it's an admirable effort. And it's not something that is just happening with Clodudy or just happening in astrophysical modeling. This is something that as data sets get bulkier and bulkier, we're living in a sort of data world now. This is a problem that happens everywhere. So these new professions that are appearing, for instance, data curation. They're looking for data curators in every field. And in science, they're already talking about data science. So in this sense, or this spirit of data science, I'm going to talk a little bit about what atomic data quality means, or what it relies on. So these are the issues that I will talk about, and the data bone of my talk. We will go with along, and we will talk about them as we go along. So we will talk about data curation. As I say, this is like a new profession. And if you look at the research enterprise, there are like different levels. You can talk of 3 levels. So the classical level is the black arrows. You have a scientist, he's doing a research, and he generates like primary data, which becomes derived data, and eventually it goes through peer review, and then it's published, and hopefully it will get to the libraries and to the users. He also generates data set, and research can be done with those data. So it's a database research, and that can go along these red arrows, similar way. They can, go to the publication channels and things. The third level, which is what we're talking about now, is based on data collections. And that means that the scientist then has to be in touch with somebody that will prepare these collections of data, or integrate these collections of data, or manage the data so they can get into these special repositories so they can be used for further research. And I think the way things are going and the amount of data that is being generated, this is going to become a very important set. So they rely on these data repositories. I mean, we have evolved from data banks, databases, and now we're talking of data repositories. So we'll talk a little bit about these distributed and interoperable data repositories. Perhaps you've been acquainted with the Virtual Observatory. And we'll talk a little bit about VAMDC and AtomPy, which have to do with atomic data. This is VAMDC, the Virtual Atomic and Molecular Data Center. This is a fairly large European effort led by Marie-Lise Duvernet from the observatory in Paris. Involved several European countries, Russia, Serbia, India, South Korea, Brazil, Venezuela. The idea is that you have a virtual warehouse that contains more than 15 atomic and molecular databases. And they're all kind of in this virtual environment, which can be accessed without having to worry about data models, notations, technicalities. Somehow it has a front end that would make life easier for the user. I mean, these points were mentioned in the previous talk. And what comes out is also pretty standard. They have something called exams, which is a specially custom-made XML schema that allows to emphasize things like data provenance, data methods, etc. So they can be used either by clients using a web interface or by actual applications. So this is a sort of pretty fancy thing and allows one to use these databases, and they're also trying to make them a little bit more interoperable. So this would allow you to cruise between databases without having to know much about how to do it and how to query them. This is also, this is what we call AtomPy. This is something that we proposed a couple of years ago to do with data assessment. The difference between data assessment and databases is that basically you don't want to discard data. You want to have them side by side so you can decide how to decide what are the better ones and what the problems are. And what we decided here, what we were proposing, the data curation and assessment model is rather than being based on one expert giving a certification, a data certification, it's community driven. So it's a little bit like Wikipedia in the sense that it's open and everybody contributes, and progressively the data or the knowledge, it becomes sort of close to what it should be. And the other thing is based on virtual research communities. They're virtual because they're all scattered around the world. You don't want them in the same institute, and somehow they have to communicate, have meetings, and decide. So this is a space to do that. It's an open space. You put data side by side, and it's based at the moment on Google Drive, Google Spreadsheets, and Python Pandas data structure. That's what we call them, AtomPy. That will allow you to download data sets from the cloud onto your local computers. Just to give you an example, well, these virtual communities we're talking about, I also emphasize that there will be, or there have been, from different disciplines. I will give you the short story about the research to do with astrophysical opacities. In 1982, this guy called Norman Simon, he proposed, or he made a plea for a revision of the metal opacities. In fact, he was saying that if you took what was at the time the standard opacity from Los Alamos, you couldn't solve a lot of problems in pulsation stars like Cepheids. And if he multiplied his data set by a factor of 2 or 3, he could solve most of these problems. So he would ask for that. And this challenge was taken by 2 groups, the Opacity Project, which I took part, led by Mike Seaton, Dimitri Mihalas, other persons like that, there's somebody else, David Hammer, and that's one of the teams. And that was based on, state-of-the-art computational atomic physics methods like the R matrix, which, in a way, having configuration interactions allows you to reconstruct the whole bound state spectrum and all the resonance spectrum of all the ions. And particularly if you're going up in Z along an isoelectronic sequence in which all these resonances, they move down and they become bound states. And as they go around, they produce all these crossings, level crossings, and that changes all the radiative properties. So with this method, you can be able to sort of reproduce them. The other team was Opal from Livermore, Forrest Rogers and Carlos Iglesias from Livermore Laboratory. They used a simpler approximation, single particle parametric potentials. But in a way, by having a simpler method, they could have the bookkeeping, how many transitions they could incorporate. That was an easier problem, or something easier to manage. Also, the equation of states were different in these 2 methods. We emphasize a more sort of chemical picture. We're dealing with atoms. The people from Opal, they had a more sort of a collection of particles, so that's more sort of a physical picture. 5 years later, some preliminary results told the whole problem. This is the monochromatic opacity from Los Alamos original, which were the standard opacities of iron, and the new results had this bump here, which were produced by 3-to-3 transitions in ions. And that was what was the main problem with these opacities. And once we had that in hand, we managed to compute reasonable data. And as time went by, the agreement after 10 years was really good. We're talking in the sense of 10 to 20%. However, some years later, people from Opal criticized that we had not included inner shell transitions. They were absolutely right. So we did a second lap, including these transitions. And certainly they made difference at high temperatures and high densities. Here we have the Rosslyn mean as a function of temperature, and then you can see with and without these things. This revision that was done, there was a lot of expectation for them, because that same year, 2005, there had been a revision of the solar opacity, the solar abundances, revision down by a group, Asplund et al., by doing photospheric models, including granulation, hydrodynamic, and the line formation in convective cells. So they did a very thorough job. And the abundances, particularly of the volatiles, carbon, nitrogen, oxygen, neon, they went down. And that made people connected with solar models very upset, because they had before a really excellent agreement with the high helioseismology benchmarks, which is mainly the depths of the convection zone and the abundance, the helium abundance on the surface of the sun. And before they had, these 2 results from helioseismology, And this is a solar model with the opal opacities and with the OP, and you can see, pretty good agreement. So once you brought the new Asplund et al. Abundances, which are these two here, and the agreement just went off. So they're really upset. So the trick here is that the abundances go down, the opacities must go up. So in a way, there's something missing there. And if you had a 10 to 20% agreement between two groups, figuring out what was missing is not sort of that easy. Another benchmark from the helioseismology people is the sun speed profile in the sun. And here they have plot the differences between modeled and observed. You see the radius of the sun. As you can see, as you get to the depths of the convection zone, with the new abundance that you get this really big disagreement. Before, this is what it was before, and this is what it was the new one. So what the people, the helioseismology people, Christensen, Dalsgaard, and collaborators did is, in the same way that Simon did before, is, what is the increase of these new opacities in order to solve their problem? And what he found is that the changes were little, 14, 15%. It's not like factor of 2 or 3 before in the Norman Simon days. So it's little, particularly in the outer layers at low temperatures, and as you go to the higher temperatures of the solar core, you're talking about 2%. So that gives you an idea what the new things are, and actually finding that 15% is become quite a difficult thing. Another thing that these people did is, if you can see here very close to the solar core, there's also a bit of a difference with the new abundances, and what they actually did, in the same way that they increased empirically the opacities, they increased the nuclear rates in order to agree with the solar neutrino measurements. And you play around and say, well, this is the new rate that we need in order to comply with that, also with that benchmark of the neutrino fluxes. So as you can see, these opacities, and these nuclear reaction rates are very temperature dependent. So the opacity also plays a part there. So we have these two benchmarks, the helioseismology and the neutrino, and this is the environment in which we have to increase the opacities. You're finding the opacity increases, but they're pretty, constrained. Well, these problems with the solar abundances the solar is quite a difficult thing. Before they had a solar neutrino problem, and now they had a solar abundance problem. And what it has, it led to all sorts of new developments. For instance, with the solar model, they now talk of doing more dynamic model, including rotation, diffusion, mixing, convection, overshoots, magnetic effects. The nuclear reaction rates have been improved. Theoretical and experimental opacities. This is what we've been involved with. There are several groups doing these. There's also the helioseismology in order to determine the helium surface abundance. They can tap or gauge the equation of state, so it makes a decision which is better, whether you have the chemical picture or the physical picture. Also, the helioseismology is a very powerful method, and they have extended that to asteroseismology, in other words, to other stars. And with all these planetary explorations now, that's becoming quite an attractive field. And they're doing these, with different stars, metal pulsars, V-type pulsators, in which they have like hybrid oscillator modes. And that data is also telling that the opacities are not quite right. So, it's not just the solar problem, but there's something not quite right as yet. This is measurements. For the first time, people from Sandia use Z-pinch plasma apparatus. They've been able to get measured opacities, and here we have the opacity of iron in similar conditions to the convection zone, and they obtain an increase in the right direction, perhaps not large enough to solve the problems. And the problem here is that the theoretical results which you can see here is the OP, the opacity. These are new kids in town, the atomic from Los Alamos now, and there's some French groups here, and somehow they're quite below that. And as you can see, it's not only the absolute value, but they have windows. These windows here are too large to help. So there's also a problem of all the theoretical camp to actually comply with these new measurements. So the point I was trying to make is that the computation of obtaining these atomic data for astrophysical applications is like a never-ending story. I mean, 20 years later, we're trying to solve something that appeared at first sight to be all right. And it's becoming a discussion now of very sophisticated research fields, as we had seen. And this is the way of the interaction in order to solve problems in all the camps, particularly also with these astrophysical opacities. Well, in that sense, we've done, in order to help this interaction between different disciplines, we did a blog. We called that Astroatom, that was proposed in a meeting in Tenerife some years ago. Jorge Garcia Roja, who's here, was part of that. Gary himself put a hand. Manuel Bautista, who was mentioned today. Valentina Luridiana, who's no longer with us, but she's gone to other fields, but she also helped. So the idea is have a discussion, and you will get on Twitter new papers and things. There's also called Nebulatum. This is a school on emission line objects that we have been organizing with Gracina, who's here, and Christophe, which we emphasize both the modeling and the atomic physics. This is, again, Clodudy-based. We have other powerful tools, Python tools like PyNeb, PyCloudy, that we also use, and the students quite like as well. And the important thing here is that this interaction between atomic physics modeling is a good opportunity to discuss some of the problems in the field and things. And it has encouraged me to get a little bit more involved, actually from data production to actually getting involved in the modeling. And this is the time that the kappa distribution came, and I got involved with this kappa distribution. The kappa distribution is to do with some people they reckon that the problems between the cell and the ore discrepancies can be solved with non-Maxwellian electron distributions, and the kappa is a way of doing that. And that implies then getting involved, before you can test whether these kappa distributions work, actually working out what the accuracy of the atomic data really is. So that's what I've been doing, and just again getting involved in benchmarks. Benchmark is to do with actually reproducing or choosing a spectrum and trying to figure out whether the actual atomic data is working. So one chooses a good spectrum and just trying to solve whether the A values or the collational data are all right. And this has been done extensively by the Chianti people. That's one of the reasons why Chianti is also becoming a popular database. Particularly Giulio Del Sana, Helen Mason. And what they do, they define an emissivity ratio, which is basically the observed intensity divided by the level populations, electron distribution, the A values. They have a C constant, which normalizes. The idea is to get that close to 1. And basically, you do that for every transition that you observe for this ion. They do it for solar lines, extreme ultraviolet, particularly from iron, so nickel and things like that. So they have a lot of lines. And the ideal thing is that you have something like this, and they have a crossing here that will give you the electron distribution. In practice, what happens is that you get something more like this. This is ion 10. And I mean, you have some good results here, but then you get this sort of behavior. And that could imply probably a misidentification or blending and things like that. And it could be problems with the observations. We have an example here, ion 14, and they have this sort of behavior here, a bit too broad. And some earlier measurements or earlier observations they get something a bit more like that, which is more satisfying. So that means that not always the latest measurements or observations are the most accurate. This is an observation from the 1973. Also, it could mean probably in the atomic data. This is IF-17, and this is what they had using the data from Bathier and Dorshek. And when they use more recent data by Liang and Badnall, they get something which is a bit better. This is your 10% thing in which you would like your things to agree. So this sort of approach led us to somehow do something similar with the data more to do with nebula lines. And this is from a paper by Mendoza and Bautista, in which we were testing the kappa distribution. And what we did here is instead of selecting the most accurate collisional data, we discarded some, but we used, for each ion, what was available, 2 or 3 data sets, and we computed the temperature for a sample of galactic H2 regions, and you figured out by using these different data, what type of dispersion you will get with the temperature. And what we found with all these usual diagnostics is that the error in the temperature is very similar to the observed, or to the error that was obtained by only assuming errors or uncertainties in the observations. This is in Orion. I put Orion is much darling in this meeting. This is the measurement, the observation by Esteban et al. And as you can see, the dispersion or the errors are very similar, the same magnitude. So what I was trying to convey is that this observation errors and these atomic data errors, and I think these latter ones have not been taken too much into consideration. It's like a black box, and when they assume there is no error there, and as you can see, it's a bit of both. And we went into the kappa distributions. Here we put these diagnostic diagrams that have been shown here previously. It is with nitrogen 2, oxygen 2, and sulfur 2. And the black line here, or the black points, is the Maxwell-Boltzmann locus. The red and the blue points are kappa distributions. I think it's 20 and 10. And here we have an observed point. And basically, you could say that you could solve. I mean, the temperature of these 2 points, they could be the same if you have a kappa distribution around 20. But the errors in the nitrogen 2 observations are too large to be able to say anything definite. So the error in the observations here doesn't allow you to kind of, say anything, with certain degree of certainty. And as you can see, we could estimate an error of the Maxwell-Boltzmann distribution, but not of the kappa one. So that encouraged us to do a bit of math. They were complaining of not getting enough equations in the presentation. So what we tend to do is to work out what is the impact or the propagation of the errors of the atomic data on the level populations and on the line ratios. So we take the statistical equilibrium equation and we can work it out. And this is for a Maxwell-Boltzmann distribution. And we can also done it for a kappa distribution. So we can work it out. So you end up with things like these. This is a bit of a continuation of the work by Binet et al., in which we are trying to reconcile the sulfur 3 and oxygen 3 diagnostic temperatures. As you can see, this is the Maxwell-Boltzmann, and then these with the different kappas. But as you can see now, we have an error band in these things. And for oxygen, we have a good error of 10%. They're fairly accurate, recently resolved by Story et al. But for sulfur 3, we estimated from the Mendoza and Bautista paper an error in the collisional data of 25%. And that makes life here is, the diagnostic loses its effectiveness. And I would say beyond 12%, I mean, between 12,000 degrees, cannot use it. and you cannot tell whether it's a difference between Maxwell-Boltzmann or kappa distribution. So in a way, the atomic data uncertainties are limiting the effectiveness of the diagnostic and the possibility of telling whether it's a Maxwell-Boltzmann or a kappa distribution. And as you can see here, this is one of the samples we took. This is from Valley Asari et al., provided us by Gracina. These are giant H2 regions, and this is the sulfur-3 temperature and oxygen-3 temperature. And you can see the magnitude of the this is only taking into account the atomic data problems. These error bars are too large to be able to, to say, well, we can move up these points with a kappa distribution, but the errors perhaps are just too large to be able to whether this is a reliable procedure to do. We also done that with the helium-like triplet. It's used a lot in X-ray astronomy. This is the G temperature-dependent diagnostic. This is between the in the N=2 atomic complex. This is the forbidden plus intercombination line over the resonance line. Is temperature-dependent. It was proposed by Gabriel and Jordan in the 70s. It's a very powerful diagnostic, and this is again with a kappa. We estimated all the errors particularly from Keenan and Agarwal collaboration, and again you can see beyond say 5 megakelvin. I mean, it loses its effectiveness, and you cannot tell the difference between kappa. As one tries to benchmark this atomic data with other data sets, immediately you begin to, some of the calculations begin to leak, or you see errors. This is a problem by the Leheyen et al. And this is a plot called the Burgess plot. Gary mentioned Alan Burgess from his earlier Cambridge days. And here one is plotting the temperature from 0 to infinity in a reduced scale from 0 to 1. And you can estimate the points at 0 and 1. And you can see there's a lot of a good agreement here, but this calculation is quite out. This is neon 9, sorry. And as you can see, this is the calculation by Chen et al., which is the one used by many of the databases. I think maybe Gary uses it in Clodudy or Chianti, AtomDB, and they're quite faulty. And that's what we have shown. As you go to this diagram, this is for magnesium versus silicon plane. And here is the blue, again, is the locus of Maxwell-Boltzmann, and these are the kappa 20 and 10. And these are the measurements from stellar corona. And the point we're trying to make here is that the errors are too big to be able to say anything. Probably you can say statistically these two ions are in the same plasma, but you cannot tell whether it's Maxwell-Boltzmann or. And I think the errors introduced by the kappa, I mean, if you take into consideration again the problems with atomic data, they're small, the deviations. Another benchmark that we did with these helium-like ions is with the tokamak. The interesting thing about tokamak is that instead of using the line ratio to determine the temperature and density, the temperature and density were measured by alternative methods, and then they measure the line ratios. So what we did in our models is just to put these two temperatures and see if we can agree with their line ratios. And what we find here is that we were a little below measurements and a previous calculation by Keenan et al. And the reason for this is that our plasma model was simpler. We were only using a collisional radiative model, not including recombination. And one can tell there's a little bit of a contribution there. And the point I was trying to make is that some people say, oh, this is collision dominated, or this is a photon, recombination dominated. And the point is that I think you have to do both. You cannot always, choose one or the other. You have to always do both, because the contribution, they may be small, but they're there. And perhaps this is a message that should also be taken into consideration in nebular physics. You cannot always say this is collisional excited lines and recombination, because there's a bit of each in every. this is a problem to do with ion 3 that came into my mind, to my knowledge, from Christoph in one of those nebulatum after hours. And he said there was something wrong with the atomic data. And this is, we use observations from Orion, Herbig-Haro 202. There's a paper, a poster here by Norberto Espiritu. They've done similar things, and they know the importance of having a good ion abundance. And basically, we're using two data sets, collisional data sets, one by Badron and Balance, and one by Bautista et al. Christoph has mentioned that the Bautista et al., using his fancy PINEB diagrams, are not, there was something wrong with them. And in fact, he was right, because the main problem, rather than being absolute poor data, is that they have problems with level indexing. And this is something that happens not only with the atomic producer, but also with people doing models, getting the levels in the right order and with the right assignation. And once one does that, you get something which is reasonable. I mean, there are still differences. So the differences in the collisional data, they mainly show up in the density, and it's the difference between the blue ones and the red here. And the atomic data, the relative data, is a difference in the temperatures. And here we use 4 data sets. And the message there is that most people, or they've been using the atomic data set from the collisional targets, and for these ions of iron, which are forbidden lines with very small A values, that's not good enough. You have to use, a little bit something more sophisticated, and this is what Depp and Hibbert had done. They call it fine-tuning, and once we did that, we agree with them. So it tells a bit of a difference. If you go to this emissivity ratio diagram, this is for ion 3. So as you compare with what we saw before, there's something not quite right here as yet. I mean, you can see the crossings for different densities, and what we had done, we kind of averaged them, but they're not crossing at the same point. So maybe this is a problem. Still, there's something problem with the atomic data, or there's also a problem with the observations. So this is what we have been working on. This work that I've been mentioning, it's had a lot of students, 3 students working on it: Joel Baker Rodriguez, Adriana Garcia, and Alejandra Hernandez, who some of Gracina knows, who took part in Nebulatum. So they've been the ones that have been doing this work that I have mentioned. Well, finally, just to leave you a message, a bit speculative. I think we should start thinking about artificial intelligence. In IBM in the early 80s, we were already talking about expert systems. Now, I think they call them machine learning systems. But the point I was trying to make is that they're beginning to use them. And I think we should, keep an eye or begin to make inquiries about it, because they can be used for 3 things in our field. These calculations that we do, you have to be a real expert to do that. Lengthy, bulky, so we can use a machine to do that. Just teach them as an expert to do these things. The other is the data analysis that we do these, which means to go to the ADS for new data, BAMDC, where we talk to these data comparison environments, Canty, to the actual codes database, etc. Or if a user says, what's the quality of a data set for this particular ion, and this system could reply, almost in a verbal mode, what the situation is. That's another one, the data analysis. And the third is actual coding. They're using artificial intelligence to code. And it is easier to have a machine coding, perhaps they do it better, than actually doing the coding oneself. Coding has always been very sort of human, busy enterprise, full of mistakes, errors. You've seen it with Astro H. The problem with Astro H was not the hardware, but just software problem. You can teach a machine to actually, develop code. So I think this is something that once you keep an eye on, in the field of data science, this is already happening, and perhaps we should, begin to think about it more, inquire. Just to finish, This thing is, I mean, what happened? Can I have my last slide? My conclusions, or my final remarks. I think I've been trying to convey to you that atomic production and dissemination is keeping up with the recent developments of data science. Atomic data assessment is likely to be carried out by multidisciplinary communities, virtual communities. Benchmark, which we've been trying to do, just compare to see whether the actual data actually works. It's a convenient way to guarantee data availability. And here in Gary's presence, who's been a staunch, what would you say, skeptical of kappa distribution, of non-Maxwellian distributions? I would say at least due to the atomic data uncertainties, nebular electron distributions remain Maxwell-Boltzmann. Thank you.
There is time for one question or comment.
Well, we were very optimistic about just grabbing external databases in Cloudie. Cloudie is no better than the external databases, and we kept tripping over gross, horrendous errors in the atomic databases. One very famous database featured negative collision strengths, which we detected within a millisecond, because we detect that. And they'd been happily computing negative collision strengths for 20 years. And so we do this in-house. This is life itself, is the atomic data. It's no better than that. So I don't know there's any way that I would ever give over our life to a database that is coming in off the web with gigabytes of data that's not perhaps been checked for negative collision strengths.
Well, these data that I mentioned of Neon 9, they did not compare with Sang and Samson data that have been there since the 70s. And they could have done that and would avoid to publish faulty data, you see? And in that respect, Gary, I think something which has been good is that somehow taking the Cloudie database from the actual code to having it in it separate.
Well, we've done that. That's called the Stout database.
Exactly.
But that's because it's a beer, not a Chianti. So
But in a way, then the Cloudie database becomes an important database, you see? And that should be, it should be able to be accessed independently of the Cloudie code.
Well, you don't need to, because our Stout database is a carbon copy of what we download off the journals. That's a feature of it. So you can get a bad NEL data file, and that's our data file.
But your database has been debugged, and that's an important thing. So it has a value, and we've done that with XStar. We separated the database from the code. We call, I think, they call it the Universal Database, UDB, I think they call it, and that is an additional database that people can use. And I think the Cloudie database, it's got a value by itself, and for all this work you've done.
Let's thank Claudio again, please. For you.
Where is it?
This
Okay.
one, this one, and this forward and backward.
Oh, okay.
This is the pointer.
All right.
So now we have David Lambert, who is going to talk stellar compositions and atomic data.
Well, thank you. Thank you to the organizing committee. Especially I'm delighted to be here to honor Gary Ferland. I've never used Cloudie. I may still use it, but I would claim that just like the Big Bang, which had an origin, I would claim to be close to the origin of Cloudie in the sense that I helped Gary with Nova Cygni 1975. I don't think I was in the dome the very first night when a phone call came in. I think my colleague Jocelyn was there. In those days, we worked from a room below the dome floor, and we communicated with the night assistant via intercom. And Jocelyn said, next object, number 24 on the list. And the night assistant, Martin Villarreal, came over the line. No, 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 we're going to another star. And this was the first time in the history of long working with the McDonald night assistants that we had the night assistant tell us what to observe. But that was Nova Cygni, and that was the birth of, I think I can claim, the birth of Cloudie. So I was there almost at the origin. I'm not talking about the title in the program, so the word aura is sort of incorrect there. You don't get a choice of whether I talk about stellar compositions and atomic data. I'm going to choose to talk about lithium and some observations and puzzles. This is a view of our 10-meter telescope, the Hobby-Eberle telescope, and McDonald, as traditionally known, is sort of in the direction of the projector. All right, so now if I can, there we go. I'm going to talk about lithium. Its atomic and nuclear structure greatly constrain and help us interpret our observations of lithium in the universe. In addition, lithium is very much a trace element, so there's a limited number of areas in astrophysics where we can get observational constraints on lithium. It's very important to understand the atomic structure. The lithium atom is an alkali, it has a low ionization potential. Its resonance doublet is at 6707 angstroms. It's the equivalent of the sodium D doublet. Remember, the sodium D lines are split by 6 angstroms. The 2 lines in lithium are split by 0.15 angstroms. So in all but interstellar conditions, you see the lithium doublet as a single line, but it's actually made up of 2 principal components. In addition, they have hyperfine components. For astrophysicists, it's irritating that if you remove 1 electron from lithium, you get a helium-like, and if you remove 2, you get a hydrogen-like ion. And from your very first experience, lectures on atomic structure or quantum mechanics, you appreciate that the resonance lines of helium-like and hydrogen-like lithium are going to be totally unobservable, and they're way, way, way down in the wavelength. So that means that all observations of lithium have to be obtained essentially via the resonance doublet. And since it's a neutral atom of low ionization potential, you're limited to observations in warm or cool stars and diffuse interstellar clouds. There are a few cases of lithium-rich cool stars where the abundance of lithium is enough that you can observe a couple of multiplets from the upper state of the resonance line. So they would be excited lines. Oops. The nuclear structure is such that the synthesis is very difficult. And you may remember from nuclear physics, there are no stable nuclei with mass numbers of 5 or 8. If synthesis is difficult, destruction is very rapid inside stars. You get protons, and lithium-7 and lithium-6 can be very rapidly destroyed. So that means that there's net stellar synthesis in only special stellar environments. If you have a convective environment, you could conceive, and we'll talk about it later, of a stellar hot interior where lithium can be manufactured, and then convection carries the material out rapidly enough into the cool envelope and atmosphere where the lithium can avoid destruction by protons. Or you can make lithium in explosions, such as novae and type 2 supernovae, where the manufacturing site is part of the explosion, and in that way you avoid destruction. What is it? This is way too sensitive. There we are. I'll talk first about synthesis in the interstellar medium, which is possible because we have cosmic rays permeating the interstellar medium, energies of 40, 50 MeV per nucleon. The cosmic rays hit, shall we say, an ambient oxygen-16 nucleus, and at sufficient energy, it can split off bits of oxygen-16, and such a bit may be lithium, beryllium, and boron, and then there are some fragments left over. In addition, you can have collisions between cosmic ray alphas and interstellar alphas, which can give you lithium-6 and lithium-7. The original proposal for interstellar medium goes back to this paper by Reeves, Hoyle, and Fowler, Galactic Cosmic Ray Origins of Lithium, Beryllium, and Boron in Stars. And there's this delightful quote by Hubert Reeves in 1993, where he said, I won't imitate his French accent, but in 1969, I presented these ideas in a seminar at the former IOTA in Cambridge. During my seminar, Fred Hoyle kept on talking to Willie Fowler. I could overhear some of his words. I have been repeating that to you for many years. You should have listened to me. Later on, he told me, Hoyle told me that he had considered this scenario for a long time, and we published a paper, this paper, on it. Now, Reeves's insistence on this being a good idea came from his knowledge, which wasn't limited to him, but came from his knowledge that in the galactic cosmic rays themselves, the abundances of lithium, beryllium, and boron were really much higher than in the interstellar medium and comparable to the carbon, nitrogen, oxygen abundances. So he knew from talking to colleagues in the cosmic ray field that the galactic cosmic rays contained products from these kind of spallation and fusion reactions. Nowadays, I suppose, people don't talk during seminars. They're too busy looking at their email on their laptops. Okay. In the observations in the diffuse interstellar medium, which we and others have done, you need to appreciate that the lithium line is a weak absorption line, partly because lithium is a trace element, 1 part in 10 to the 9 relative to hydrogen. And lithium is mostly ionized because of the low ionization potential. But in order to get the lithium abundance, you've got to correct for the ionization, which I think is difficult, not impossible, but can't do very precisely. But what you can do really quite well, if you get good enough data, is measure the lithium 7-to-6 ratio, which in meteoritic materials is something like 10. We have found a couple of line of sights near a supernova remnant where the lithium 7-to-6 is 2, demonstrating galactic cosmic ray spallation in action. There we go. So we have 2 stars here, 2 lines of sight. On the left-hand panels, we have observations of a potassium resonance line, a weak line. And notice the y-axis, 1% is almost the length of the box. If at zeta per, we have a single line. We need this comparison to measure the structure of the clouds between us and the stars. And then on the right-hand side, we have the lithium observations that we made at McDonald. But now we're resolving, or almost resolving, the resonance doublet. So here is the stronger line, here's the weaker line, and if we had one isotope and there were no saturation, which there isn't at this level, this would be twice the strength of that one. Now, the lithium-6, the stronger component, is almost superimposed on the weaker lithium-7 component, and then the weaker one is over here. So if lithium-6 is very low in abundance, these 2 lines should have a 2-to-1 ratio. So you can see that's got 2-to-1, which means the lithium-6 content is very low. We go down to a micron per. The potassium structure is a little more complicated. You can see a hint of a second cloud in there. But here's the lithium, and this is clearly not 2 to 1. And so this indicates there's a substantial fraction of lithium-6 in here, something like 7 to 6 of 2. And we now have a second line of sight towards the same supernova remnant. So this is our evidence that in the interstellar medium, in the right places, you can make excess, or the clouds make excess lithium-6. Now, for stellar synthesis, the principal mechanism is what has become known as the Cameron-Fowler mechanism, which relies on this reaction here, helium-3 alpha-gamma to beryllium-7 at temperatures of 10 million degrees or greater. This is fragile, like lithium-7, and the electron captures to lithium-7 half-life of 50-odd days. So what you've got to do is to get this, the beryllium-7 and the lithium-7, out to temperatures less than 3 million degrees. So this is one of the mechanism that works in convective environments. The other point to note is that the helium-3 reservoir in the stars is partly the primordial helium-3 that has come from the Big Bang, and partly the helium-3 that may have been synthesized in the star itself by the early steps of the proton-proton chain. Once the star has left the main sequence, even for low-mass stars, this helium reservoir cannot be replenished. The time scale for producing helium-3 is too long. So observations in normal giants, when the star leaves the main sequence, becomes a red giant, it develops a deep convective envelope over roughly half the mass of the star. That dilutes the surface lithium abundance by 60-fold. So the normal lithium abundance in a star right now is 3.3 on a log scale. So it goes down to 1.5. Many giants have lithium abundances less than 1.5, which we attribute to extra lithium depletion on the main sequence. 1% of giants are lithium rich, which means greater than 1.5, and the worst case, or the best case I know, goes up to 4.2. So here on the left, we have a lithium resonance doublet from a star we've recently worked on, and this lithium, you can see this lithium doublet is a nice strong feature going down to 40%. On the right-hand side, I have an HR diagram. These are the masses of the stars, and the main sequence is down here. This star on the left is that red dot there. The blue stars came from a survey that I did with colleagues in India, who have a nice telescope at 15,000 feet in the Himalayas. Fortunately, you operate it from a ground station in Bangalore, India, so you don't go to 15,000 feet. But you can see there are lots of these blue points, and we'll ignore the green ones and these ones up here. So where might lithium be manufactured? Remember, these are only 1% of K giants. There are two possibilities. There's this line along here where the star going up this way encounters a mean molecular weight gradient, and that has been considered to lead to extra mixing, and the helium-3 gets burnt to lithium-7, or beryllium-7, lithium-7 gets convected to the surface. There's also the stars. This is the helium burning region, generally called the clump, where stars spend a couple of 100 million years, and you can see that the blue points plus our friend there line up pretty closely with the clump there. So there's still a debate unanswered about whether this, what's called the luminosity bump, is a principal way to get helium-3 to lithium-7, and or the clump is. Then there are a couple of stars over here, that's these two up here, which were way too cool. So how do these get over there? So if some young mind wants to pursue this, there's a puzzle there as to where the lithium-7 comes from. So what are the origins? It's possible that you can raise the lithium to some extent by ingesting planets. If we get rid of enough planets, we dull the interest in exoplanets. The other possibility is in one form or another to exploit, and I'm sure this is true, to the Cameron-Fowler mechanism. You can ingest a planet, and that leads to mixing. So the lithium in the planet's not the relevant thing. It's the planet or the brown dwarf leads to mixing. It can either occur at the luminosity bump, there's something called thermohaline mixing, or I just like the helium core flash and or helium core burning. And then there's luminous AGB stars. An AGB star is the next stage to becoming a planetary nebula and becoming within the realm of cloudy. An AGB star consists of a white dwarf, generally a carbon-oxygen white dwarf, surrounded by a thin helium shell, and then a very large outer convective envelope, which generally starts off, of course, hydrogen-rich. So you have a white dwarf the size of the Earth, half the mass of the star, and then you have an envelope the size of the Earth's orbit around the sun, containing the rest of the mass. These stars, the helium shell burning gets triggered in pulses. The helium shell burning leads to carbon. Some of the carbon can be dredged into the envelope. Addition of carbon into the envelope can drive the carbon-oxygen ratio greater than 1, and you have a carbon-rich star. If the star gets luminous enough, the base temperature of the convective envelope can be sufficiently hot to burn CN cycle, so the carbon gets burnt back to oxygen, and the hot bottom convective envelope can turn the star back to oxygen-rich. And then in addition, if the temperature gets hot enough, if at this temperature, the lithium production proceeds by the Cameron-Fowler mechanism. So you can generate a lithium-rich AGB star. And here's a couple of figures from a very nice review by Amanda Caracas and John Latanzio in the Australian journal. If you're interested in low-mass star evolution, nuclear synthesis, I fully recommend it. These diagrams are for a 6 solar mass of a Z of 0.02. And on the right in here, you have a graph showing the base temperature. And this is only 70 million years on the right-hand side here. We spoiled the laser? Oh, never mind. So you can see the base temperature going up to 8 million degrees, and where the horizontal, the constant strips are, that's where the base temperature is between the thermal pulses. And then on the right, we've got the lithium abundance on a log scale, and the time scale. Oh, thank you. Now it's all beyond me because I've got two things to hold. Oh, thank you. So here, and then this is the lithium abundance. This is the 1.5 or so that it gets as a red giant following the initial dilution. It then goes down, and now you can see the lithium abundance going up, and it goes up and down in here during the thermal pulses. But this time difference in here is shorter than what's over there. So you can see here the lithium abundance goes up, but the base temperature remains hot enough that the stuff that's coming into the fresh stuff coming into the envelope is lithium-3 free. So the lithium abundance declines. And this is because the helium-3 reservoir is limited. Okay, so a few years ago, we did some observations of several stars in the Magellanic Clouds, luminous AGB stars. So here's one. This is a titanium oxide band, and this line in here shows the lithium doublet. So in this star here, you can see a very strong lithium doublet go down in luminosity, and there's no lithium doublet in here. One of the nice things about observing lithium is that you get the excitement at the telescope. I mean, you could observe this star, and you can immediately see on the screen it has no lithium, and then, you know, the next object, you've got this whopping lithium line. There's lots of things in stellar spectroscopy where you can get excitement at the telescope, and then all terrible spectra like Weigel's blobs. So there's no reason, if you're interested in stellar spectroscopy, to turn to theoretical work. Here we have a quasi-HR diagram. This is the bolometric magnitude. This is the period. These are Myra variables. This is the period, and these are evolutionary tracks, I think, from Peter Wood in Australia, 2, 4, 8 solar masses. The filled, the open symbols in here are the lithium-3 stars, as sort of judged by the spectra on the left. And then the filled symbols are the lithium-rich ones, the circles being oxygen-rich and the triangles being carbon-rich. So there are very few carbon-rich stars down here. And then all the luminous AGB stars are oxygen-rich because of the hot bottom convective envelope. And they're also lithium-rich as well. So this was... Okay, we'll get there. So there's something called the new process, new for neutrinos in supernovae of type 2. You get a flood of neutrinos at the supernova explosion. The flood goes out through the star, and then in the helium shell, oh dear, now we're behind. There we go. Some of the helium splits to helium-3, and then you get the helium-3 beryllium-7 as before. This process can also produce boron-11 and fluorine-19 from carbon-12 and neon-20 in the helium, in the carbon shell. So these are rare processes. The cross-sections for these processes are very low, but it works because there's an enormous flood of neutrinos, and secondly, we're not trying to produce an abundant element, we're only producing a trace element. This is problem number 1 in the lithium world for the Big Bang. The nuclear synthesis in the Big Bang with the baryon-photon ratio coming from the cosmic microwave background, and with deuterium conformation is 2.66 or thereabouts. In warm metal-poor dwarfs, we've got the Speed plateau going back 30 years, where the number is something like 2.2. 2.2 is not 2.6, so then there's been enormous scratching of heads as to why 2.2 is not 2.6. Some people like abundance errors in these objects. Some people like nuclear physics operating to reduce this figure in the Big Bang. Of course, some people like either non-standard Big Bangs or non-standard particle physics, and there are even some people who like non-standard this and that. These are sort of stars which are 10 or so giga-years old, so it's not inconceivable that over 10 giga-years, 2.6 got reduced to 2.2, either by destruction at the bottom of some a surface layer, or the lithium has gone out of the atmosphere by diffusion. And there's some very nice work on globular cluster stars from the turnoff to the RGB by people in Uppsala, where they measure not only the lithium abundance from the turnoff to the RGB, but they measure, for example, calcium and iron abundances. So if lithium diffuses out of the observable atmosphere, iron and calcium diffuse out as well, but when you look at the red giant branch stars, the convective envelope has brought that diffused iron and calcium and lithium back to the surface. So there are 4 papers on 4 globular clusters, and they sort of argue that they can explain their observations if they start with an initial lithium abundance of 2.48. So 2.6 plus or minus something, to my mind, is close enough to 2.48. And okay, and now we've... So this, of recent years or recent weeks, this has been, to me, one of the more delightful surprises. This has got nothing to do with us. This is by Tajitsu and company using the Subaru telescope. But it's on a nova, and it goes back to the birth of Cloudie. This is a short segment of the wavelengths 3115 to 3125 angstroms, which is where the resonance lines of beryllium-2 are found. And this is at plus 38 days from the explosion of this fellow, 47, 48, 52. So let's concentrate on this panel in here, where at this phase, you get an absorption line contribution in addition to these emission lines. So the two beryllium-7 lines, the stronger one is there, the weaker one is there. This little thing here is related to that chromium-2 line. And then there's another redshift, blue-shifted component of beryllium over here. And the isotopic wavelength shift between beryllium-7, which comes from the Cameron-Fowler mechanism, and normal beryllium, which is beryllium-9, is such that the lines would be this beryllium-7 line would be sort of, this one would be centered somewhere there. So by measuring the zero velocity for these systems using sodium D or something, you can clearly distinguish between beryllium-7 and beryllium-9. So this nova explosion led to the conversion of helium-3 to beryllium-7, and if we could find a narrow absorption component in 100 days, 200 days, this lithium-7 would have gone away, and we'd have a lithium-7 rich object. So this is delightful. And then lithium has also been seen in a nova, another nova. This one's V1369 Centaurus. I don't show you the spectrum. But then this group in here do galactic chemical evolution, which is something that I think should be banned, like sort of too much drinking and driving or something. So here is the Spete Plateau. These are stars in here. These are generally disk stars. Some have depleted lithium as dwarfs. So what you're looking for is the envelope like that. So you want to go from Big Bang, put in the supernovae, novae, red giants, whatever else, and you want to be able to reproduce this curve. Now, this group, they claim that all sources except novae would give them this red line. Then they take lithium, how much lithium do they get in there? Novae, how many novae are there, etc. And so according to them, if you add the novae in, you take the red line, add the novae contribution, and lo and behold, you've explained what we think of as the observed envelope in there. There are other papers, particularly by Nikos Prantzos, where he ignores the novae and gets as good a fit to the data as that. So, as I said, galactic chemical evolution. Okay, I have to finish by mentioning emission, at least in this conference. This is the only case I know of lithium resonance line in emission. It's a hot R Corona Borealis star. Here it is. These stars are formed by the merger of two white dwarfs, helium white dwarf dumping material onto a carbon-oxygen white dwarf. So somehow through that process, it manufactured just a little bit of lithium and allows me to talk at this symposium. And then finally, one of my recent books for bedtime reading is this book by Matthew Spender. He was the son of Stephen Spender, an English poet. Stephen Spender had a good friend, Oxford friend, W.H. Auden, who was a better-known poet. And Matthew Spender met Auden after Auden had been to a Nobel symposium, mainly made up of scientists. And Auden came back, had dinner with Matthew Spender and his wife, and explained, Auden says, yes, we have a duty towards the molecules. We are neglecting that duty. And then Matthew Spender says, do you mean that the molecules which in the marble of a sculpture by Michelangelo are happier and better molecules than the ones that are still in the marble up in the quarry? Auden shut his eyes and smiled ecstatically. Yes, he said. Michelangelo, I suppose he used chisels for his sculptures and brushes for his paintings. Cloudy is essentially a set of chisels and brushes of great complexity, but those chisels and brushes allow us to understand better the stars, the nebulae, the galaxies, and hopefully the galaxies, the nebulae, etc., are happier and better molecules than the ones that cloudy and the telescopes have not yet looked at. Thank you very much.
There is time for one question or comment.
I was under the impression that there were a couple of very lithium-rich carbon stars. I think one was WC Cas.
Yes, you're absolutely right.
What's the explanation for that large amount of lithium?
The explanation is that you can generate lithium from helium-3 faster than you can decrease the carbon abundance. So it's not the case that, you know, I mean, it's still you've still got to get, the star has to get the timing right, but it's lithium-rich and carbon-rich are not exclusive. I mean, are not mutually exclusive.
Any other question or comment? No? Okay, let's thank David again. Please. David. Thank you. Sí. ¿No tienes un cuchillo? No, aquí tengo esto. So now Leticia Juan de Dios Tomás is going to talk about uncertainties in atomic data.
Well, thank you, everybody. This is a work that I'm doing along with Mónica Rodríguez at INAOE in Mexico.
Más fuerte. ¿Te dejo esto?
Bueno,
¿Subes?
No. Bueno. I don't know if you heard, but I was telling you that this is a work that I'm doing along with Mónica Rodríguez at INAOE. And it's about exploring how the uncertainties in atomic data affect our calculations of chemical abundances. As Claudio said in his talk before, computation of atomic data is a really hard work, but also the selection, determining which atomic data we should use is also a tough work. And that's why the selection of atomic data is one important source of systematic uncertainties in our determination of chemical abundances in photoionized nebula. Because these determinations depend on the values of the electron temperature and density, which are obtained by solving the equation of equilibrium statistics. That's why a single set of atomic data can affect all of our calculations, and all the different combinations affect our determinations in a very complex way. In this plot, I show you the differences from the mean for the collisional strengths and transition probabilities for transitions which have more than 2 atomic data determinations available in PINEF. As we see, the majority of the differences are within the 10%, but in some cases, these differences in the atomic data are bigger, and our main goal is to explore how these uncertainties or these differences in the atomic data propagate in the determination of the physical conditions and chemical abundances. To explore this matter, we have selected a sample of 36 planetary nebula and 8 H2 regions, which have available optical spectra deep enough to allow the measurement of a large number of lines, mostly of them collisional excited lines. The objects in this sample cover a wide range in characteristics such as excitation degree and density, and therefore can be considered as representative of the population of ionized nebula. Also, as we only want to ascertain what's the effect of the atomic data, we are not considering the errors or the uncertainties associated with the line intensities. And we use the atomic database available in PINEP and assume that the statistical dispersion from the different calculations, different results of multiple calculations by different methods and from different authors reflect the uncertainties associated with the atomic data. This table shows the ions that we are considering in our calculations. We have selected these ions because with them we can determine the temperature diagnostics and temperature and density diagnostics, as well as the ionic and total abundances of the most common elements. We perform all the combinations of atomic data, and we obtain a distribution of results like this one. This is an example of an object of the sample, NGC 6572, but the behavior of the other objects in the sample is very similar. In this figure, I'll show you the distribution of results from all the different combinations of atomic data. And the lines and numbers help us to identify which set of atomic data is introducing which differences according to this table. These numbers. From this figure, we found that the majority of the dispersion from the different density diagnostics comes from the atomic data used for the corresponding ion. And some atomic data determinations introduce larger differences. This plot shows also the distribution of results for the electron temperature from the same object. And well, as I mentioned before, the density and temperature are obtained by solving simultaneously the equation of statistical equilibrium. So part of the distribution in the density comes from atomic data used to determine temperature, as well as the dispersion in the temperatures comes from the atomic data used for the density. And in the case of the oxygen, the majority of the dispersion of the spread is from atomic data from this ion. But in the case of nitrogen, the spread is also increased by atomic data from density. And this figure helps us to see that the complex interplay between this atomic data, because most of the spread observed in the ionic abundances comes from the atomic data used to determine the physical conditions. And for example, the atomic data for oxygen 3, which is used to determine temperature, is also affecting the ionic abundances of neon and argon. And this behavior we also observe in the total abundances. So we have measured the total spreads, the total widths of the different distributions for the density, temperature, ionic, and total abundances, and observed trends like this one. In this plot, I show the total widths of the differences in our results for the density diagnostics as a function of the logarithmic of the median density. And we can see that for the sulfur, oxygen, and chlorine at low densities, around less than 3,000, the width or the total dispersion is almost constant. But as density increases, also the differences in our results increase, and reaching factors of nearly 4. And in the case of the argon, we obtain almost a constant dispersion, but this is an effect of a certain set of atomic data that always returns higher densities. This figure is similar as the previous one. In this case, we are plotting the total widths of the temperature distributions as a function of the median of the density. And in the case, for both temperatures, nitrogen and oxygen, we obtain differences of less than 10% at low densities. But in the case of nitrogen, the differences starts to increase as density increases due to the dependence of this diagnostic with density. And in the case of the ionic abundances, as these parameters depend on the calculations of the electron temperature and densities, here's the combined effect of the atomic data from temperature, density, and also from the ion that we are calculating, the ionic abundances. And although not all the ionic abundances reach the same, have the same differences, in some cases it reaches values of higher than 1 order of magnitude. As well as in the case of the total abundances, although these determinations depend on the ionization correction factor selected, we have differences of nearly a factor of 6 that even if we change the ionization correction factors that we are using, it's hardly likely that this dispersion will be reduced for objects with high density. So we conclude that the selection of atomic data cannot be disregarded because it introduces larger differences, especially in high density objects, in which for the ionic abundances, the differences are nearly of a factor of an order of magnitude, and the total abundances of a factor of 6. And we are also trying to estimate how to reduce these differences or determine which set of atomic data we should use by doing these 2 things. Thank you.
Thank you. Questions for Leticia? Comments?
I think it's very, very important work. There was a paper about 10 years ago by Mike Barlow and others at UCL. They went through the selection of transition probabilities, and you would think that for forbidden lines, the most recent paper would be the best paper. And what they did an analysis similar to what you had, and they cherry-picked the very best transition probabilities, and they found that often it was Claudio's 20-year prior work that was much better than the most recent work. So it's very much your next step of selecting out the best matching data is going to be a big step forward. And the surprising thing is that frequently the newer papers are not actually as good as a paper 10 or 20 years before. That was the conclusion from the Barlow work. So very nice. Thank you.
Any other question for Leticia? I was going to ask this also, if we can choose some atomic data, but you are working on.
Yes, we're working on that.
Mm-hmm. Okay.
It's possible that some of the difference are because the lacking of some atomic data in the question that you have processes in some databases that you don't have in other databases.
Could you repeat me the question?
So, for example, no, you have some citations in some databases that they are lacking, they are not there in other databases, and that is making the thing. So it's that you have a fundamental process that is not there. That's possible?
Maybe it could be possible, but I'm not sure if I understand what's your question. But because if I understand what you're asking me if I'm not considering some transitions in the same databases, and that these differences is what causes the difference in the results.
Yeah, there are some processes that are not there.
Well, but could be possible, but it also depends on how the atomic data was calculated.
Okay, any other question? Okay, let's thank Leticia again. And before leaving, we have one announcement.
Yes, just an update for those of you that were interested to go to the sculpture exhibition. I'm told by the locals that we don't need to buy the tickets ahead of time, so we just buy them there. I think we can maybe leave a little bit before 5 o'clock, but I have to confirm this, maybe 4:45 in the bus. So if you want to go, then I guess we meet outside. One other thing, hope you don't mind, but you have to give me 50 pesos, $3, so that I can pay for the bus driver to wait for us and then take us to the hotel afterwards. So if you don't mind that, yeah. Oh, we will be there for approximately 1 hour. We can actually reduce that a bit depending on what time we arrive, but apparently it's not far from here. It's fairly close. So maximum 1 hour. We should be back in plenty of time, at least an hour before the dinner. So it shouldn't be a problem. Thanks.
So thank you all again. And we have coffee now. Some more announcement? No? Okay. So please come back at 4 o'clock. No? Yes.
Bueno. Bueno. sí.
No, ahorita que
No, sí, pero sí.
no, pero ve haciéndolo ya, porque debes empezar a la hora.
Ok, oye, solo una pregunta. Ellos están quedando detrás. ¿Es una?
Está justo enfrente de...
Sí, sí, sí. No, mi anuncio va a durar 30 segundos. No, no, no.
Sí.
¿Ya? Con calma.
Está ajustado.
Okay. Hello, everyone. Okay, can I have your attention, please? For those of you who are not going to the Anish Kapoor exhibition, us, the local students, would like to show you around our university. I don't know if you noticed, but the National University, the Central Campus, is our World Heritage Site. There are some really cool murals and interesting buildings that you would like to see. We would like to show you around, and after, when the lecture is over, we're going to walk from here to the main campus. So if you want to come see it with us, join us at 4:30. Okay, thank you. Well, we'll show you the way to your hotel after that. Okay, thank you.
Okay, so we have the last talk of today by Gustavo Bruzual, who is going to talk about modeling the nebular emission from you changed the title, no?
Yeah, you can.
From primeval to present-day star formation galaxies.
Using Clodudy.
Using Clodudy.
Well, as everybody else, I also want to thank the organizers for allowing me to speak here in this very well-organized meeting. It was the opportunity to meet Gary Ferland. I haven't met him before. I will be speaking about a recent work that I have been doing with these collaborators that you see here. And we are trying to put together the population synthesis models with a code like Clodudy to study distant galaxies. As you know, in a few months, the observing proposal for the new space telescopes are due. So we are trying to be ready to interpret the data for the next the GW Space Telescope. So this we need to do this in 3 steps. First, we have to refine and rebuild the stellar population synthesis models to make them up to date and to become state-of-the-art population models. Then we have to use this is very confusing. Use Clodudy to compute the nebular emission that we expect from the gas that will be in a galaxy, which is also a state-of-the-art nebular emission model. And then we want to compute the spectra of the stars plus gas plus neutral ionized gas and the effect of the dust, everything in galaxies in general. So we want to put everything together. What's the motivation for this? Why do we care about new population synthesis models? These have been around for a long time. Well, first of all, as you know, there is a lot of people computing new evolutionary tracks all the time. There are new observation of stars, so things keep improving all the time. So we want to take the latest data, the latest available information, and build the best models possible. Also, in the literature, there are many codes to derive information of the spectra using what is called now SED fitting. And in particular, the Bayesian approach is becoming very popular. And one of our collaborators developed a code called Beagle, which is here the reference. And we want to have a good input for this kind of code to try to derive the best possible answer for the SED fitting problem. And finally, we want to derive, this is the final goal, get information on the nature of the star formation and the interstellar gas in distant galaxies, which is interesting. So to this goal, we will work with the new evolutionary tracks and the most spectra we can find in the literature. For evolutionary tracks, we are using this recent work by Bressan and collaborators. Chen is a student of Alessandro Bressan. This is good because they have ultraviolet stars in the evolution, which, as we have heard many times, are very important for studying ionizing environments. And also, for the lower mass, we have to use also the Bressan tracks, which include the treatment of the thermally pulsing AGV stars, that, as you may have heard, is a real problem in this kind of models. These tracks are very complete. We have here 15 different values of the metallicity, which we have complete set of tracks. There is one more that is not plotted here, so actually we have 16 values. The HR diagram for every metallicity is very complete. There are more than 26,000 points in the HR diagram. And it's very finely divided in the metallicity in metals and helium, so you have to make a choice and whatever. There is too much information there. See, this is a set that we finally pick up. Then you go to the stellar libraries, and we have now many possibilities. We are using all of this in the ultraviolet. In the visible, we have this. One important thing is, since we are using the Wolf-Rayet star, we have to have a good model of the stellar atmospheres of the Wolf-Rayet star, and we are using the best models, or the only models there are. This is from the Potsdam group. It's called power models. I will show some of them now. In the optical and visible, you already know this. In the infrared, there is still some important data. It's good models. So in general, we are putting together whatever is available, and we think that they are working fine. These power models, I guess most people here must know it because you are interested in ionizing stars. They are very good, and they come for different Wolf-Rayet stars, and they are available only for these 4 metallicities. So yeah, you can see immediately that we have to make some compromise because we are using these values of the metallicity for many more metallicities, higher than lower than this. And this covers this wavelength range. I will show here some results of use. This is the UV range. You can see from very low 100 angstroms to 1,000 angstroms. I will go, this is starting, you will see in different colors, if you can see the colors at all, the contribution of the main sequence and of the Wolf-Rayet stars. At very young ages, this is 0.5 million years. This is a simple stellar population. As we go, you will see that these kind of things that appear here are the Wolf-Rayet star. So they, as you can see here, the purple color is the main sequence. In the top panel is a model in which the higher mass in the main sequence is 600 solar masses. So this is an exaggeration, and this is the 100 solar mass sort of a standard model for the IMF. But the important thing here is that we see a lot of light here that is not due to the main sequence, it's coming from the Wolf-Rayet. And this is the important part is that this lasts very short. I mean, it's a few million years. Right? At 6 million years, in a simple star population, the Wolf-Rayet are gone. So if you want to pick them up in a cluster or something, it's very unlikely because they don't last anything. If you use a constant stellar population, that means that the main sequence stars are continuously replenished, and they will always be dominating. You get also the Wolf-Rayet on top of the main sequence, but never in such a domination because the main sequence stars are also bright in the UV. But still you will see some features from the Wolf-Rayet. In this case, I am dividing the Wolf-Rayet by all the different kinds. If we add them up, the plot looks, the spectra looks nicer. So this is a simple population in which we have the main sequence in purple and the Wolf-Rayet star in blue. So you see that there is a lot of activity in this spectral range. When we go to the constant population, the situation, as I said, is different, but still we have some contribution from the Wolf-Rayet. From this kind of model, you can derive, obviously, the number of ionizing photons, and this is hydrogen, helium-1, helium-2. So these quantities are now very well determined with these population models. This is just like a digression going to the infrared, which very few people have talked here, but as you know, there is a lot of problems in the stellar synthesis models with these TP-AGB stars because there is very little data. The evolutionary tracks are not very good. So somehow we have to test if what we are doing is relevant or not. For those of the students or those of you who don't know, the TP-AGB stars sit here in the HR diagram. These are post after the AGB phase. So this is an enlargement. The AGB stops here, right? So after the AGB, we have the oxygen-rich stars that will be here, more or less. The carbon-rich stars in the same place, but even cooler and brighter. And the superwind phase of the TP-AGB, which is even cooler and even brighter. So the position here is just where they are in the evolutionary tracks that we are using. But obviously, they are very cool. They have expanding atmospheres with a lot of dust. So the spectra that they will have has nothing to do with the temperature that you're observing. So somehow we have to, what we do is we compute we use a code called DUSTY to compute the emission that you expect from the synchrostellar dust. And then you have to compare if what you are getting looks like real or not. So one way to compare is that we do this comparing with the luminosity function of the TP-AGB stars in the LMC. And there is a lot of information here. I don't expect you to follow all of that, or just I want you to see that the color histograms fall very well inside the black line, which is the black line is the observations. So in a way, this is telling us that we have the right number of TP-AGB stars, that they have the right colors, that the dust effect is taken into account well enough. This is a 3.6 microns magnitude. And also for the SMC. So in a way, these models are good. I will say from the far UV to the near infrared, they are quite competitive. So you can trust them and use them with confidence. Now, we want to do some application to the real world here. And that's what we are using Clodudy for. This is like a cell-consistent modeling of the spectra and the nebular emission lines in star-forming galaxies. So we want to model the emission of the gas that is ionized in a spiral galaxy, a star-forming galaxy, using as input our spectra and as output what Clodudy tells us that it should be. We have to make many, many assumptions that they are explained in this paper, which is already accepted. You can look this in the archive. And the idea, our main interest is to try to use this in distant galaxies. So, well, this is quite straightforward. Our spectra, the scale here is too big. It's a model. It's not a black body line. Here is a lot of information. We input that into Clodudy, and Clodudy tells us, the real spectra is the red line. And then we will have to see. This is a lot of work. It's a PhD thesis of the student from France. These are all the parameters that she's using, all these metallicities, the ionization parameter, all these possible values, the dust to metal ratio, dust to metal mass ratio, this quantity, the gas density, these different values, the ratio of carbon to oxygen, to different values of the upper mass in the IMF. So when you combine all of this, you get several tens of thousands of moles. So it's a big computation. It takes a lot of time. So this, I will show some 3 or 4 plots from this work. We have here is what we are using, all these metallicities. So the points here are color coded according to metallicity in here. This is nitrogen over oxygen in the gas over the oxygen abundance in the same gas. So we want to compare if what we are using is looks like anything real. So we have here the data from M101 from Keniko is the diamonds that you see somewhere here. The pluses are starburst galaxies, and the solid dots, which are here, are from starburst nucleus from these authors. Here the models go like this, and increasing carbon over oxygen will go in this direction for a constant metallicity. And the dust metal mass ratio increases when the symbol gets bigger. Right? So we get all these predictions are in color, and the observation, you can see that at least we go from, this is like 1, 2, 3, the green line is 0.02, 0.04. So these kind of objects are consistent with anything in this metallicity range, which is quite large. Right? But we are not seeing anything very metal poor. That's well known already. More interesting is this kind of results. This is all cloudy output, actually. So we get this for these diagnostic diagrams. A lot of information here. Again, are you there? I went too fast? No, it's okay. We have here the increasing U is in this direction. When we increase the oxygen 3 in this direction, we are increasing the ionization factor. Then, again, the dust metal increases in the same way. We have here some observations, which is this gray cloud of points. These are star-forming galaxies. This should be 28,000 or 2,800. There's a 0 missing here. So we have all this data from the Sloan, which is consistent with having an interstellar medium more metal rich than 0.04, which is the same that we were looking in the same plot. And here we have like a standard model, which has these probabilities. It's close to solar. Now, besides the problem that Claudio was telling us, people that do these tracks, they now talk about the initial solar abundance and the final solar abundance, or the surface solar abundance, which they claim is 0.14, even it was 0.17 when it started. So the important thing is that at least this kind of model can explain many of these galaxies as we see in the Sloan survey, for instance. This is going to distant galaxies. We have here some points, and these are ultraviolet lines in the rest frame. So this is diagnostic diagrams for ultraviolet. And we see here some extragalactic H2 regions in gray, these gray pluses. Yeah. And some gravitational lens, the red ones. There are still some predictions here. So in principle, and here was the effect of increasing the value of U. These are helium lines, carbon to helium, carbon 4 to carbon 3. So the expectation is that these lines will be visible in distant forming galaxies or primeval galaxies that you see at very high redshift, and you want to quantify to say something about the properties of the stars that are in this galaxy. The expectation is that this kind of model will help us quantifying these kind of properties. And we are somehow satisfied that this kind of simple-minded model at least predicts line ratios that are more or less consistent with what we observe in real galaxies. Now, we want to complicate this a little bit more. So we want to model the spectra of the stars plus the neutral ionized gas using this, what I showed before, plus a model of the galaxy in which we take into account what are the effects that the gas, the neutral gas in the galaxy will have in this radiation. There will be dust, everything. So there is a code like Clodudy, but it's called SynSpec, that allows you to make models on interstellar medium, and then we can try to build some even simple-minded models, but in principle will be useful to study large sample of galaxies or distant galaxies and derive their properties. This is work by Alba Vidal Garcia. It's a student from Spain. The idea here is that we have the stellar population from our model. The ionized gas is like Clodudy telling us, and this called SynSpec, which is the neutral gas. So when we put everything together, we should get a spectra of the star-forming galaxy with a given star formation rate and given mass, etc. And from comparison of this model, but observation of this kind, we hope that we will be able to tell what are the most likely values of the parameters or physical parameter of the galaxies that we are studying. For that is that we plan to use this code Beagle that tells us in a Bayesian way what are the best values or the best physical parameters that will describe this kind of spectra. So it's very ambitious and very naive, but that's the way that this field started. And you have always a very simple-minded beginning, and it has been more and more complicated and more successful as time goes by. These are some of the predictions that we can do with these kind of models. These are the detailed spectra, and we can compute. These are line strength index in the ultraviolet, the Fanelli index. So we have the different components, the stellar, the emission, etc. So this will be a lot of effort, but I think it will be compensated. Before I forget the models, if anyone needs or wants to see what these models tell us, they are available, the line ratios or the luminosity in the lines from this page. So you can download it, or eventually, very soon, we will release the population synthesis models, and you can do as you wish. So my conclusion is that the prospects are very good in the UV and infrared. I think we are getting ready to study the new kind of information that we will be getting in the very next years with the new space telescope. Has been considerable progress in the evolutionary tracks and the spectral libraries, as all of you know. The observation have allowed us to calibrate and understand better the stellar population synthesis models than ever before. When I started in this field, this was just like, I don't know, there were 3 or 4 galaxies that you could compare the observations. They didn't match, I guess. Now the models are turning out very useful to estimate the interstellar physical parameters in the UV that determines the UV emission in the red frame of the galaxy and the emission line properties for distant galaxies. I didn't mention it well, but this observation by Stark and Toll, these are very low mass galaxies, dwarf galaxies that are gravitationally lensed, so they're quite distant. And we can try to derive what are the physical properties of these tiny dots that we see in the image. And also these models, the population synthesis plus Clouddy, are allowing us to explore the limitation of the direct temperature method to estimate the galaxy interstellar metal abundance at metallicities that are not too far from solar or subsolar metallicities, which we expect to be the case in primeval galaxies. So, well, I invite all of you to either use these things or improve it or ask for a reference or whatever. Thank you.
We have time for some questions.
Well, it's an impressive result that I have to digest. Yeah. But I want to ask you, what happens if you have spatial resolved information like with IFUs and the kinematics of the gas and the stars is different? How you will treat that? Because what you're doing is a spectral fitting that is consistent, so you have to somehow...
I think you will have to go pixel by pixel and do the same thing you do now with the starlight by using this kind of model. So because we are making a very simple assumption, like all the stars are inside a gas cloud, a spherical cloud, and so we don't have a spatial resolution so far. I will say that each pixel you have to, or each region in your galaxy will have to be treated differently. So
yeah, but if the gas that is ionized does not move in the same way that the stars, then how you have to degrade the spectra somehow to force that the gas and the stars are at the same velocity.
Yeah, you mean motion?
Yes.
We are doing this statically. I haven't thought about that.
Okay.
But in principle, you will have all the ingredients to build the things. I mean, we cannot do it completely general to have a star here and the gas moving at this, but now it's static.
Okay, thanks.
It's a very nice piece of work, but you've been really studying on low metallicity, and if you keep going in a starburst and go the other direction, I think your calculations are going to trip over a long-standing problem in ionized models of nebulae. When you get to H2 regions with metallicities of above about 2 times the metallicity of the sun, the solution changes, and it's very cold. It's about room temperature, and it only radiates in the infrared, or the O3, O4 infrared lines. Rob Kennicott says that he would detect such H2 regions. You would see them with a pure Balmer line spectrum. So they're just H alpha and H beta. That's all there would be in the optical, and then there'd be strong lines in the infrared. So I don't know of anybody suggesting what the answer to that is. I think Jasinska has written papers on this. Yeah. It's something that's a solid prediction for 30 years. If you get an H2 region above about twice solar, it should be room temperature or below, and it should radiate only in the infrared. So if you go to the other end, if you go higher, you'll trip over this, and the predictions will be infrared lines and Balmer lines.
Yeah, we have to keep going to the infrared. We haven't computed at least we haven't. This is in Clouddy, but we haven't taken this out yet. It's not in the tables. But it's a good point. We have to generalize. It's a reality.
Where are the H2 regions with above twice solar metallicity?
I don't know if there are any.
What is the mass range of the galaxies that you are putting in this program? From how many millions of solar masses to how many?
No, we normalize everything to 1 solar mass. And then
one solar mass.
This is the standard model that we use, and then you scale it as you wish.
Okay, but one would expect the small mass galaxies to evolve slower than the more massive ones, I would think.
Yeah, well, we have some. I guess you can choose some of these parameters to favor one of your galaxies. Playing with the metallicity and whatever. And what we are we only vary in mass is this, the IMF. I guess, I mean, this is just a first attempt. As we have good, some observations, we will have to start constraining this and making intelligent fits or machine-oriented fits, as Claudio says.
Any other question? No? If not, thank Gustavo and all the speakers of the session. And see you in a couple of hours in the conference.
Yep.